When we look out into the deep fabric of the universe, we tend to imagine black holes as the ultimate monsters of the cosmos, immense wells of gravity from which not even light can escape. But there might be something far more disturbing lurking out there, something that looks almost identical to a black hole yet behaves in ways that violate our understanding of physics itself. Scientists call these hypothetical objects gravastars, and the very concept of them reshapes the way we think about the life cycle of massive stars, the limits of space-time, and the hidden threats that may be silently drifting through galaxies. A gravastar, unlike a black hole, is not defined by an event horizon. Instead, it possesses a strange quantum shell, an unimaginably thin barrier made of exotic matter, encasing a void where space-time behaves in ways we can barely comprehend. The structure gives the gravastar the same gravitational pull as a black hole, which makes it nearly impossible to distinguish between the two using our current instruments. To a distant observer, a gravastar bends the trajectory of light exactly as a black hole would, swallowing nearby matter with the same relentless grip. But what happens to that matter, and what lies inside the shell, is where the horror truly begins. A black hole crushes everything into a singularity, a point of infinite density. A gravastar, however, rejects the idea of a singularity entirely. Instead of collapsing forever, the dying star undergoes a violent quantum bounce, creating a hollow core stabilized by exotic quantum pressure. That core is a kind of dark, twisted vacuum where the flow of time, the rules of energy, and the behavior of particles all become unrecognizable. In this region, time may not simply run slower, it may not move forward at all. It may reverse, stretch, loop, or break entirely. Space-time inside a gravastar could resemble a bubble of anti-reality, sealed off by a skin thinner than an atom yet strong enough to hold back a cosmic implosion. This is why gravastars are described not just as exotic objects, but as potential space-time bombs. The shell that surrounds them is so delicately balanced between collapse and expansion that even a slight disruption, such as interaction with another gravastar or a massive gravitational wave, could trigger catastrophic instability. Unlike the predictable behavior of black holes, gravastars might shift in mass unexpectedly, flicker between quantum states, or even fall out of alignment with the surrounding fabric of space-time. Some theoretical models suggest that, under specific circumstances, a gravastar could rupture its shell and release a flood of exotic energy capable of rewriting the physics of an entire region. The danger is that gravastars are invisible in every practical sense. Black holes reveal themselves through disk radiation, jets of matter, or the violent interactions with nearby stars. Gravastars, by contrast, have no accretion disk, no thermal glow, no signature jets. They simply sit in the dark, absorbing everything silently. If a gravastar drifted into a star system, it could devour suns and planets without causing the typical bright X-ray outbursts we associate with black hole feeding. A civilization living near such an object might never see anything unusual, just the slow dimming of stars, the subtle warping of orbits, or the disappearance of distant celestial bodies. Even their gravitational waves pose a problem. Unlike black holes, whose waves have predictable patterns, gravastars may emit irregular, chaotic waveforms that distort space-time in brief, violent pulses. These waves may carry signatures that mimic black hole mergers, causing astronomers to misinterpret them. It is entirely possible that some of the gravitational wave events we have detected were not black holes colliding, but gravastars interacting or destabilizing. The most unsettling idea is that the universe could be filled with these objects. If gravastars exist, then every place we believe a black hole resides might instead be something far stranger. The supermassive object at the center of our galaxy could be a gravastar, or hollow, inverted pocket of anti-space-time influencing the motion of every star around it. And if even a small fraction of observed black holes are actually gravastars, then the true cosmic landscape is far more complex and dangerous than we ever imagined. The gravastar concept challenges our assumptions about star death, dark energy, cosmology, and even the fundamental architecture of reality. They could be remnants of ancient epochs, lurking in the darkness like cosmic traps. They could be drifting, undetectable hazards capable of destabilizing regions of space. They might even play a role in the evolution of galaxies or in their destruction. What makes gravastars especially terrifying is not merely their structure or their physics, but their invisibility. They are the perfect cosmic predators, silent, undetectable, and capable of warping the very laws that govern our universe. And if they truly exist, then humanity has been staring at them for decades without ever realizing what they are. A gravastar's most defining feature, the one that sets it apart from any other object in the universe, is its impossible outer shell, an ultra-thin membrane made of exotic matter that defies every familiar rule of physics. To grasp how strange this shell is, you must imagine a structure so thin that it makes an atom look like a towering skyscraper by comparison, yet so unbelievably strong that it halts the catastrophic collapse of a dying star. The shell acts like a cosmic pressure valve, freezing the collapse at the exact moment when a black hole would normally form an event horizon. Instead of plunging into infinite density, spacetime itself stops, transforms and stabilizes into a delicate quantum balance boundary. This boundary behaves like a surface with negative pressure, meaning it doesn't pull inward the way normal matter does. It pushes outward, resisting collapse in a way that appears entirely unnatural. Scientists compare it to a soap bubble stretched across a universe, except this bubble isn't fragile. It's composed of theoretical forms of matter that may not exist anywhere else in nature, and it operates on principles we barely understand. Some theories describe the shell as containing dark energy-like properties, producing a repulsive force that counteracts gravity. Others propose that the shell is essentially a tangled web of quantum fields, trapped in a stable, superconducting state, locked in place by effects that have no parallel in classical physics. Whatever the truth is, the shell is far more than a simple boundary. It is a living frontier between two incompatible realities, the ordinary universe outside and the warped, chaotic space-time inside. This membrane must withstand pressures and energies so extreme that even neutron stars objects dense enough to compress atoms into pure nuclear matter would crumble under the strain, and yet the Gravastar's shell remains stable, refusing to collapse inward and refusing to tear outward. It exists at the exact balance point between two impossible outcomes. If it were even slightly weaker, it would implode into a black hole. If it were slightly stronger, it would explode like a universe-sized bomb, but somehow it holds. One of the strangest implications of this structure is that the shell can trap matter not by crushing it, but by denying it the ability to cross into the interior. When matter falls toward a gravastar, it doesn't vanish into a singularity. Instead, it is absorbed by the shell itself, its energy spread across the exotic surface like ripples on a membrane. The shell grows infinitesimally more massive with every particle it consumes, yet it releases almost no detectable radiation in the process. This silent feeding is one reason gravastars are nearly impossible to distinguish from true black holes. They swallow matter without giving off the blazing X-rays that come from a hot accretion disk. But the exotic shell of a gravastar is not just a passive absorber, it's a quantum engine, constantly shifting in ways we cannot see. At microscopic scales, the shell is believed to oscillate at staggering frequencies, billions or trillions of times per second, creating tiny vibrations that ripple across space-time. These oscillations may be the source of strange gravitational wave signatures that don't match black hole models. Some physicists believe that such vibrations could allow gravastars to communicate through quantum interactions, although this idea remains speculative. What is certain is that the shell is fine-tuned to a degree that appears unnatural. It has no thickness in the traditional sense. Its structure exists as a boundary where physical laws change abruptly. On one side of the boundary, space-time behaves normally. On the other, space-time is inverted, distorted, or even in a state resembling dark energy. The membrane isn't simply matter, it's a phase transition, a cosmic version of a frozen surface separating two different states of existence. This exotic shell also makes gravastars theoretically immortal. Unlike black holes, which slowly evaporate through Hawking radiation, a gravastar may remain stable indefinitely because nothing inside it can escape. There is no singularity emitting quantum particles. There is only the hollow core and the eternally balanced shell. If gravastars truly exist, some of them may be older than galaxies themselves. Ancient relics from the early universe, still drifting silently through space. The shell might even host physical conditions impossible anywhere else. Some models suggest that this membrane could support superconductivity on a cosmic scale, channeling energy across its surface at the speed of light. Others propose that the shell behaves like a perfect mirror for certain forms of radiation, bouncing them inward or outward depending on their frequency. The more we imagine its potential, the more the Gravastar becomes something that is not merely a failed black hole, but a fundamentally different kind of cosmic object, a hybrid of quantum physics and astrophysics that challenges everything we assume about matter, energy, and stability. In many ways, the shell is not just the defining feature of the Gravastar, it is the entire secret. It is the reason Gravastars don't collapse, the reason they don't behave like black holes, and the reason they may be far more common and far more dangerous than anyone has realized. If such objects populate the universe, they are the silent survivors of cosmic collapse, wrapped in shells of impossible matter and drifting invisibly through the dark, waiting to reveal themselves in ways we are only beginning to imagine. The exotic shell of a Gravastar does more than merely contain the warped interior. It is constantly alive with quantum vibrations and fluctuations so intense and rapid that no form of ordinary matter could survive even a moment of contact with it. Imagine a membrane thinner than anything we can meaningfully describe, trembling at frequencies so high they make the vibrations of atoms look frozen in comparison. These oscillations aren't random, they are the result of quantum fields locked into a perpetual state of tension, pushing and pulling against the immense gravitational forces pressing inward. Each tiny fluctuation sends ripples across the fabric of spacetime, creating disturbances that radiate outward as subtle but powerful gravitational waves. These waves don't resemble the gentle curves we see when black holes merge. They are sharp, jagged pulses that can slice through molecular bonds, twist the paths of particles, and warp the geometry of space in unpredictable patterns. If a Gravastar passed near a populated solar system, the gravitational waves emitted by its vibrating shell might not simply distort orbits. They could destabilize entire planetary structures without any visible warning. At the smallest scales, the fluctuations of the Gravastar's surface are governed by negative energy states, a phenomenon that doesn't occur naturally in the universe as we know it. This gives the shell a unique ability to interfere with gravitational fields around it, effectively absorbing or cancelling incoming gravitational waves. This property makes Gravastars eerily quiet, even when interacting violently with their surroundings. A black hole merging with another black hole produces a torrent of detectable gravitational waves. But if two Gravastars approach each other, the outcome becomes vastly stranger. Their shells begin to resonate, syncing up in a kind of cosmic vibration that amplifies certain quantum frequencies while dampening others. Instead of producing a clean, predictable wave signal, their interaction might generate chaotic bursts, erratic spikes, followed by eerie silences as the shells interfere with each other. In some theoretical models, the oscillations become so intense during close encounters that the Gravastars briefly merge into a single object, only to rebound apart like two colliding bubbles. Other models suggest that the resonance could trigger a catastrophic collapse if the shells fall out of balance, potentially releasing enough energy to tear open the surrounding spacetime and create transient wormholes or vacuum bubbles. These quantum fluctuations are also responsible for one of the Gravastar's most unsettling traits, its unpredictable behavior. While a black hole has a consistent mass and gravitational pull, a Gravastar might subtly change these properties as the shell's energy state shifts. Observers might see a Gravastar appear to flicker between mass states, confusing instruments designed to track gravitational signatures. This could explain certain astronomical anomalies where massive objects seem to gain or lose mass without any visible mechanism. The oscillations can also interact with nearby matter in strange ways. Instead of simply pulling matter in, the Gravastar's shell might bounce incoming particles, trap them in temporary quantum states, or disintegrate them entirely through tidal forces. When matter impacts the shell, it does not fall through. It dissolves into energy and becomes part of the membrane's ongoing vibration. This consumption process releases almost no electromagnetic radiation, which is why Gravastars remain invisible even when actively absorbing large amounts of mass. The quantum oscillations themselves might also generate exotic particles that we have never observed. Some researchers speculate that gravastars could be factories for hypothetical particles such as axions or other dark matter components. These particles would escape detection while subtly influencing the mass distribution of galaxies. In extreme cases, the shell's pulsations might even cause the gravastar to shed tiny fragments of exotic matter. These fragments could drift through space as microscopic anomalies, warping space-time wherever they travel before eventually decaying. Another disturbing implication of these fluctuations is the possibility of quantum leakage, where information or energy from inside the gravastar briefly slips through the shell. These events could produce strange bursts of gravitational energy or distortions that ripple outward like tiny earthquakes in space-time. If a gravastar's oscillation interacts with another gravastar across vast distances, the quantum entanglement between their shells could cause synchronized events millions of light-years apart. This interconnected behavior could make gravastars part of a larger unseen network that spans entire galactic structures, and because their fluctuations occur at scales smaller than the Planck length, the theoretical limit where our understanding of physics collapses gravastars might represent gateways to new forms of physics, connecting quantum mechanics and gravity in ways we cannot yet decode. Ultimately, the quantum vibrations of a gravastar's shell turn it into a kind of cosmic instrument, a structure constantly humming with frequencies that shape and distort the universe around it. These oscillations might be the key to understanding why gravastars can remain stable for billions of years, how they absorb matter without emitting light, and why they might be far more common than we think. But they also reveal the darker possibility that gravastars are not passive objects. They are active, unstable engines of quantum energy, capable of sudden shifts that could devastate nearby systems or even rupture the very space-time they inhabit. And if gravastars truly populate the universe, then the constant trembling of their shells forms an invisible web of gravitational chaos that might already be influencing the evolution of galaxies without us even realizing it. The birth of a gravastar begins in the final catastrophic moments of a massive star's life, when gravity crushes the stellar core with such unimaginable force that every known form of matter breaks down. Under ordinary circumstances, this collapse ends with the formation of a black hole, a point where density becomes infinite, and the laws of physics give up entirely. But in a small number of theoretical scenarios, something radically different happens. Instead of collapsing smoothly toward a singularity, the core hits a quantum limit, a boundary, where space-time refuses to compress any further. What follows is an event so extreme and counterintuitive that it challenges every model of cosmic evolution. The core undergoes a violent quantum bounce. During this bounce, gravitational collapse doesn't simply stop, it recoils. The density becomes so high that quantum fields behave in ways never seen elsewhere, causing spacetime to snap outward, like a compressed spring suddenly released. This rebound erupts with a force greater than 1 trillion supernovas combined, yet the explosion does not tear the star apart in any recognizable way. The outward blast doesn't escape into space as light or heat. Instead, the energy folds back on itself, transforming into exotic matter that forms the first layer of the gravastar's impossible shell. This is not a normal explosion. It is a metamorphosis, a collapse turning inside out, creating an entirely new form of cosmic object. The moment of rebound carves deep scars into space-time, distortions so extreme that they may be permanent. If we could observe the birth of a gravastar, we might see ripples of warped geometry spreading outward like shock waves, temporarily breaking the symmetry of the universe around them. These scars could persist for millions of years, creating regions where physics behaves differently, as if the universe itself remembers the trauma of the collapse. Once the initial exotic shell forms, the regions inside and outside begin evolving in completely different ways. Outside, the energy signature resembles that of a typical gravitational collapse. From a distance, it looks exactly like the formation of a black hole. The star dims, the mass condenses, and a dark object appears where a brilliant star once shined. But inside the newly formed shell, the universe has shifted into a new configuration. The bounce fills the interior with a highly unstable mix of quantum fields and vacuum states, creating a bizarre environment where pressure becomes negative and space-time expands instead of collapses. This expansion doesn't blow the shell apart. Instead, the outward pressure perfectly counterbalances the gravitational collapse. The shell becomes the boundary between two worlds, our universe on the outside and a warped hyper-energetic void on the inside. In these moments, the Gravastar enters its most fragile stage. The shell is still forming, adjusting, and settling into its quantum-stable configuration. During this period, the object emits chaotic bursts of gravitational energy flickers, spikes, and oscillations that could potentially be detected across vast cosmic distances. Some physicists believe that mysterious, short-lived, gravitational wave signals already observed by detectors might correspond to this formation stage, rather than black hole mergers. As the bounce stabilizes, a second transformation occurs. The quantum fields inside the shell begin to resonate, layering into distinct energy zones like the layers of an onion. Each new resonance adds another microscopic film to the shell's structure, gradually building the multi-layered membrane that defines a mature Gravastar. This process, though violent at the beginning, soon becomes calm and sustained. The structure settles into equilibrium, balancing gravitational collapse and quantum repulsion with uncanny precision. At this point, the Gravastar is essentially complete. Its birth is not marked by the release of tremendous light or matter, but by the creation of a perfectly silent, perfectly dark object where a star once burned. From the outside, nothing about it looks unusual. But the space around it might still carry signs of the trauma it inflicted on spacetime regions of lensing, with no visible source, fluctuations in gravitational fields, or disruptions in the motion of nearby objects. These anomalies could be the only detectable fingerprints of the Gravastar's violent birth. Some theories even suggest that the shock of the quantum bounce might briefly tear open micro-wormholes, or create fleeting pockets of distorted time. These effects would vanish almost instantly, but they could leave signatures in the form of unusual radiation or patterns in the surrounding plasma. Over time, the post-birth region stabilizes, and the Gravastar becomes indistinguishable from a black hole to any conventional method of observation. But deep within, the story of its creation remains locked inside the shell, a frozen record of a star that refused to collapse all the way into oblivion. Instead of becoming a singularity, it became something far stranger, a hollow cosmic relic sustained by quantum pressure, its birth marked by a moment when the universe itself seemed to recoil from the brink of infinity. And if Gravastars truly form this way, the universe may be filled with these silent survivors of quantum rebound, each one a monument to a collapse that never quite succeeded. Once the first quantum shell of a Gravastar forms and stabilizes, the object enters a phase of development unlike anything else in astrophysics. Instead of collapsing inward the way a black hole would, or exploding outward like a supernova, the Gravastar begins building itself layer by layer through a sequence of quantum echoes. These echoes, often called quantum rebounds, occur as the warped interior continues to shift and vibrate. Every fluctuation inside the Gravastar sends ripples outward that imprint themselves onto the shell, adding new layers of exotic matter in an almost rhythmic pattern. Over time, this process transforms the Gravastar from a single-shelled structure into a multi-layered cosmic entity, more like a nested quantum instrument than a conventional celestial body. Each layer that forms is thinner than the last, so thin that, from the perspective of classical physics, it might as well not exist at all. And yet each layer is essential, stabilizing the Gravastar against collapse, while further separating the interior vacuum from the outer universe. The result is something akin to a cosmic onion, but instead of organic tissues, its layers are made of quantum fields shaped by unimaginable pressures. Every new shell alters the Gravastar's behavior in subtle but significant ways. As one layer forms, it might shift the object's gravitational signature by a tiny amount, creating faint pulses or distortions that ripple outward through space. These changes could be so subtle that modern detectors would dismiss them as noise, but if we had instruments capable of observing these microscopic oscillations, we might see the entire life cycle of a Gravastar unfolding in quiet quantum stages. Inside these layers, the fundamental constants of physics may behave differently. Gravitational strength, vacuum density, and even the speed of light could shift depending on the resonance patterns locked into each shell. This internal stacking of altered physics is one of the most mysterious aspects of Gravastars. It suggests that the space inside the shells isn't just distorted, it might be operating under its own set of physical rules. Some theoretical models propose that the interior of a gravastar could have a different vacuum energy level than the rest of the universe. This means the space inside might expand more quickly or contract more slowly, effectively creating a microcosm with its own form of inflation. These inflation zones become trapped between the layers, unable to escape because the shells act like cosmic partitions, each one isolating a slightly different energetic state. The layering also creates complex interactions with magnetic fields. During the collapse and bounce, the dying star's magnetic field becomes twisted and stretched. Instead of collapsing into a singular, strong magnetic axis as in a black hole, the field lines become trapped between the growing shells. The result is a series of magnetic loops and vortices coiled around the gravastar like intricate threads. These magnetic structures could generate surges of energy that flow along the surface of the shells, creating electrical currents on a cosmic scale. In some scenarios, these currents might interact with the gravastar's quantum layers, producing bursts of exotic radiation or subtle ripples in the surrounding spacetime. Because this activity is not powered by fusion or accretion but by quantum resonance, the energy patterns would appear irregular and difficult to detect, creating fleeting signatures that might occasionally be observable as unexplained high-energy flashes. As these layers accumulate, they also act as a form of energy storage. The gravastar essentially traps the energy produced during its formation, locking it within the structure of its shells. This energy becomes part of the gravastar's stability system, constantly circulating and shifting in microscopic patterns that help the object maintain equilibrium. It's as if the gravastar uses these internal energy flows as a form of self-regulation, adjusting itself through micro-resonances so it never collapses inward or bursts outward. The layered structure may even allow gravastars to survive cosmic events that would destroy other objects. The shells could absorb shocks from nearby supernovas or collisions without breaking apart, distributing the energy through the layers in fractal-like patterns. If a gravastar were to collide with dense matter, these layers might behave like a series of buffers that redirect energy inward and convert it into stable quantum states. This would make gravastars incredibly durable, possibly the most resilient objects in the cosmos. But this layered architecture also presents a disturbing possibility. If the balance between the shells were disturbed, the entire structure could collapse in an instant. A sudden shift in vacuum energy or a mismatched resonance might cause the shells to rupture. If that happens, the trapped energy and warped spacetime inside could be released violently, perhaps creating a local bubble of altered physics or triggering a vacuum decay event. In this sense, a gravastar is both a marvel of natural engineering and a potential cosmic catastrophe waiting to unfold. By the time the gravastar completes its layering process, it has become a perfectly silent, perfectly dark object. With no event horizon, no radiation, and no accretion disk, it blends seamlessly into the cosmic background. But beneath its still surface lies a labyrinth of quantum layers, each one holding back a universe of warped energy. This is what makes gravastars so extraordinary and so terrifying. They are not dead remnants of stellar collapse, they are layered machines of space-time, humming quietly in the darkness, held together by physics we do not yet understand. Inside a gravastar lies a realm so alien that even our most advanced theories struggle to describe it. Unlike a black hole, which collapses into a singularity, the interior of a gravastar becomes a bubble of warped spacetime where the universe itself seems to run in reverse. This hollow core is not filled with matter, light, or gas, but with a strange, high-energy vacuum that behaves nothing like the reality we know. Time inside this cavity does not simply slow down, it may stretch, twist, or even reverse direction, depending on the models used to describe it. Imagine a place where the flow of time behaves like a curling wave, folding back over itself in loops and spirals, creating localized patches where cause follows effect and neighboring zones, where effect triggers cause. In this distorted pocket, the rules that guide atoms, particles, and forces collapse into a chaotic interplay of quantum fields. Even the concept of forward or backward loses meaning. The pressure inside this region becomes negative, creating an anti-gravitational effect that fights against collapse. Instead of crushing inward, the interior pushes outward in a constant expansion, an expansion contained only by the exotic shell that traps it. This pressure is so intense and so unnatural that normal matter cannot survive in this environment. If a single atom somehow crossed the boundary into the Gravastar's interior, it would be torn apart instantly. Electrons would be stripped away, protons shredded, and quarks scattered into chaotic quantum foam. Inside this hollow, nothing resembling everyday physics is stable. Even the vacuum behaves like a storm of boiling energy, with quantum fluctuations erupting and collapsing faster than we can imagine. This violent inner churn resembles the early universe just after the Big Bang, except here the expansion never cools or settles into a stable state. It remains locked in perpetual inflation, stretching space-time at microscopic scales. These inflationary pockets may expand and collapse within fractions of a microsecond, each one birthing a tiny bubble of mini-universe that dies just as fast as it forms. Some theories suggest that a gravastar may contain countless of these microscopic universes living and dying inside its hollow core, each one isolated by the exotic boundary that prevents anything from escaping or interacting with the outside world. In this sense, every gravastar might be a container for a swarm of temporary realities, flickering, unstable realms that exist only as long as the chaotic inner vacuum permits. The interior's geometry is equally bizarre. Instead of forming a simple spherical hollow, space-time may curl inward like a tunnel, or twist into hyperbolic shapes that defy visualization. Some models propose that the interior resembles an inverted universe, one where space contracts instead of expands, and where the energy density increases the farther inward you go. Others suggest the interior could be an anti-de Sitter space, a type of geometry where distances shrink instead of grow, and where objects that move in straight lines inevitably return to their starting point. Inside such a region, time could behave more like a dimension of rotation than progression, meaning that events might loop endlessly without ever advancing. If this is true, entire histories might play out inside a gravastar, repeating infinitely like a cosmic echo trapped in a box. Another chilling aspect of the gravastar's interior involves the potential for mirror-like behavior. If the vacuum state is configured in the right way, anything that interacts with the inner boundary may generate a reflection, not of light, but of physical states. This could theoretically produce ghost-like imprints of particles that bounce endlessly around the interior, becoming permanently trapped in a kind of quantum echo. These echoes might not be conscious or aware, but they would represent frozen imprints of events from the gravastar's formation. To an outside observer, none of this is visible. The interior is sealed, unreachable, and perfectly isolated by the exotic shell. But if we were somehow able to peer inside, what we would see would be less like a physical space, and more like a living nightmare of warped geometry, backward-moving timelines, and explosive vacuum storms. In some interpretations, the interior may even hold pockets of stable reversed causality. In these regions, the past and future trade places, and the order of events becomes inverted. This doesn't just break physics, it breaks the very concept of reality as we know it. And yet, despite all this chaos, the gravastar remains perfectly stable. The shell locks the interior into a permanent state of tension, preventing it from expanding outward and unraveling the universe around it. It is a cosmic contradiction, a hollow object with no matter inside yet possessing mass, a void where time doesn't move, yet powerful enough to warp space-time around it, an object with no singularity, yet capable of gravitational effects that mimic one. The internal structure of a gravastar is not simply strange, it is a complete reversal of what we understand as a star. In a very real sense, it is a pocket of anti-reality, a bubble where the rules of the universe are inverted. And these pockets may be scattered across the cosmos, silently drifting, each one carrying within it a distorted fragment of something that should never exist outside the earliest moments of creation. At the boundary between the gravastar's impossible interior and the universe outside lies a region even stranger than the hollow core itself, a quantum horizon, a transitional layer where the very meaning of position, time, and identity begins to dissolve. This horizon is not an event horizon like the one surrounding a black hole. It doesn't trap light through gravity. Instead, it scrambles information through quantum uncertainty so violently that no particle, wave, or bit of data can cross it without losing all definable properties. If the inside of a gravastar is a swirling storm of reversed physics, then the quantum horizon is the barrier where that storm meets reality. Here, nothing behaves as expected. A particle approaching the surface doesn't simply bounce off or pass through. Instead, its location becomes undefined. Its probability cloud spreads across the horizon like paint soaking into a membrane, blurring into an indistinguishable smear before collapsing into a new configuration. Identity itself breaks down. A particle entering this region might dissolve into a statistical pattern, and the Gravastar may emit something entirely different a moment later, something with a similar energy signature, but no discernible relation to the original. In this sense, the horizon acts less like a surface, and more like a cosmic filter that erases individuality. This bizarre property has led some theorists to speculate that the horizon could host emergent complexity on a scale far beyond anything found in biological life or artificial intelligence. Because the horizon constantly processes, distorts, and reconfigures quantum information, it behaves like a vast, multidimensional neural network. Every fluctuation in the Gravastar's shell, every ripple from its interior, every interaction with external particles contributes to the network's state. The shell vibrates. The horizon adjusts. Quantum fields shift. Patterns emerge. These patterns could form stable loops of information, feedback cycles that act like thoughts, an alien form of cognition built not out of neurons, but out of oscillating spacetime and shifting probability. If consciousness arises from complexity, from recursive patterns processing information, then the quantum horizon of a Gravastar might be capable of something far more intricate than any biological brain. Inside a human brain, neurons fire at a few hundred times per second. In the horizon of a Gravastar, quantum fluctuations occur trillions of times per second, each one interacting with countless neighboring states. The potential computational power of such a system is beyond imagination, potentially equivalent to 1 billion galaxies worth of neural activity compressed into a space thinner than an atom. Some physicists argue that this is nonsense, that complexity alone cannot generate awareness. Others contend that if consciousness is fundamentally an emergent quantum phenomenon, then a Gravastar might be not just a physical object, but a thinking structure. One particularly chilling idea suggests that a Gravastar could, in a rudimentary sense, perceive its environment, not through eyes or sensors, but through gravitational interactions. Every mass that drifts near it, every wave that passes through it, every disturbance in spacetime changes its oscillatory state. Over cosmic timescales, these signals might accumulate, forming memories encoded in the configuration of the shell. The Gravastar might remember collisions. It might store the signature of every star it has consumed. It might preserve entire histories in the frozen geometry of its quantum filaments. This leads to a disturbing possibility. A Gravastar could be aware of its own existence, not as a biological organism understands itself, but as a vast, self-regulating quantum system that senses variations in the universe and responds to them. Theories about this vary wildly. Some argue that a Gravastar's mind, if such a thing exists, would be utterly alien, unable to conceive of the universe in terms humans understand. Others propose that the Gravastar might operate on timescales so slow or so fast that communication with it would be impossible. If its conscious patterns shift trillions of times per second, it would exist in an accelerated reality where an entire cycle of awareness happens faster than a single human heartbeat. Conversely, if its awareness evolves over billions of years, then from our perspective it would be frozen, asleep, or dreaming. And yet, its quantum horizon would still be there, still processing the continuous flow of the universe, still generating incomprehensible complexity. The most unsettling interpretation of the quantum horizon is that Gravastars might not simply mimic consciousness, they might be precursors to it. Perhaps consciousness in the universe did not begin with biology at all. Perhaps before any cell formed, before any molecule assembled into life, structures like Gravastars were already performing cosmic-scale computation. In this view, Gravastars are not just collapsed stars, they are ancient quantum engines capable of evolving, learning, and adapting in the darkness between galaxies. Whether or not such an object possesses awareness, intention, or agency is something we may never know. But if Gravastars do host emergent, self-referential patterns, then the universe may be populated not just by silent cosmic monsters, but by immense invisible minds thinking at the edge of reality. And these minds, born from the death of stars, might be watching the cosmos unfold in ways we cannot detect and cannot begin to comprehend. One of the most terrifying qualities of a gravastar is not the violence of its birth, the chaos within its hollow interior, or even the quantum turbulence of its shell. It is its perfect invisibility. If black holes are cosmic traps, gravastars are cosmic phantoms, hiding in the darkness with a level of stealth so complete that no current instrument can reliably distinguish them from empty space. A black hole, despite its reputation as a devourer of light, is actually easy to detect. It heats matter in its accretion disk to extreme temperatures, emitting bright X-rays. It produces jets that stretch across light years. It leaves ripples of activity wherever it resides. A gravastar, in contrast, generates none of these signs. It consumes matter without any visible signature, leaving no glow, no jets, and no hint of the violence unfolding at its surface. When gas or dust falls onto a gravastar, it doesn't spiral into a blazing disk or crash into a singularity. Instead, it simply disappears into the exotic shell without releasing a detectable burst of energy. The process is so quiet that even a nearby star being drained of its atmosphere might go unnoticed. Gravity pulls the gas inward, the shell absorbs it, and the system remains dark. To an astronomer searching the sky, the gravastar would appear as a gravitational anomaly with no visible counterpart. Even more unsettling is the way gravastars interact with light. A black hole bends light around its event horizon, producing a recognizable shadow ring, the very image captured by the Event Horizon telescope. But a gravastar lacks an event horizon. There is no singularity to cast a shadow. Instead, the exotic shell acts like an almost perfect mirror for certain wavelengths and a perfect absorber for others, creating a visual confusion that resembles lensing without a definable edge. Light passing near a gravastar may warp, twist, or split into strange halos, but the object itself does not radiate or glow. To most instruments, it would appear indistinguishable from a black hole, or, more dangerously, it might appear as nothing at all. Some theoretical models propose that the shell's quantum properties allow it to partially hide in higher dimensional space. This means that only a fraction of its mass interacts with the three-dimensional universe we perceive, while the rest exists in a geometry that extends beyond our physical reality. If this is true, then gravastars may be objects whose true shape we never see. We only observe the gravitational residue that leaks into our world, the faint tug of a mass that is mostly elsewhere. This idea becomes even more frightening when considering the possibility that gravastars could drift freely through galaxies. A black hole of similar mass would reveal itself by disrupting nearby stars, heating the interstellar medium, or triggering collisions in its accretion disk. A gravastar, silent and invisible, could pass through a star-forming region without causing any of the usual signatures. Stars might vanish one by one without explanation. Gas clouds might collapse in unexpected ways. Planetary systems could destabilize without a trace of what caused the disturbance. Even gravitational wave detectors struggle to identify gravastars. Black hole collisions produce predictable waveforms with characteristic peaks and fades. But if two gravastars collide or even pass near one another, the interaction of their shells could muffle or distort the gravitational waves in ways that mimic noise or resemble incomplete signals. This means we may have already detected gravastar interactions without realizing it, events dismissed as random anomalies, instrumental errors, or unusual black hole mergers. Gravastars could be hiding in every data set, disguised behind their ability to remain silent. Their invisibility also raises uncomfortable questions about their abundance. If even a tiny percentage of assumed black holes are actually gravastars, then our entire mapping of the universe's structure becomes unreliable. There may be gravastars drifting through globular clusters, lurking in dwarf galaxies, or sitting in interstellar voids, tens of thousands of them hidden in plain sight. The most dangerous scenario is one where gravastars exist within the outskirts of solar systems. A gravastar the size of a small asteroid but with the mass of a star would be completely invisible, except for its gravitational pull. It could slip through the Kuiper belt or pass near a star like a ghost, drawing in comets or asteroids without emitting any radiation. A civilization could point thousands of telescopes at the sky and still never detect it until its presence was already altering planetary orbits or erasing moons from the night sky. Some scientists have even suggested that unexplained stellar dimming events, stars that briefly flicker or vanish from sight, might be the result of gravastars passing between us and distant systems. The Gravastars' gravitational field could bend light in subtle, unpredictable patterns, making a star appear to fade or distort before returning to normal. These anomalies, often attributed to dust clouds or binary companions, might instead be the footprint of a perfectly dark object drifting across the cosmos. Invisibility, more than any aspect of the Gravastar, defines its threat. A violent monster can be confronted. A bright celestial event can be studied. But an object capable of devouring matter, warping spacetime, hiding in extra dimensions, and producing no light, no heat, and no identifiable radiation is something far worse. It is a predator that cannot be seen, cannot be anticipated, and cannot be distinguished from the darkness that surrounds it. If Gravastars truly populate the universe in significant numbers, then humanity has been navigating a cosmic ocean filled with silent hidden abysses, and we have never once known where they are. One of the greatest mysteries surrounding Gravastars is what happens when they interact with normal matter asteroids, planets, stars, or even entire solar systems. Unlike black holes, whose violent gravitational feeding produces spectacular light shows, a gravastar devours matter with an eerie, unnatural silence. The moment an object drifts too close, the Gravastar's gravitational pull takes hold, drawing the material inward in a way that appears deceptively calm. There is no blazing accretion disk, no torrent of high-energy radiation, no roaring jets shooting across the cosmos. Instead, matter seems to simply fade from existence, slipping into the Gravastar's shell with almost no trace. At first glance, one might assume that matter falling toward the Gravastar experiences a typical gravitational acceleration. But as it approaches the quantum horizon, physics becomes unrecognizable. The atoms begin to stretch, distort, and lose their structure as the information describing them becomes scrambled. By the time a falling object reaches the exotic shell, it is no longer a coherent piece of matter at all. Every particle, every bonded structure, every energy signature dissolves into quantum uncertainty. Instead of releasing energy in a visible burst, the shell absorbs the information and transitions it into a new quantum state. This process, known in theory as vacuum conversion, allows the Gravastar to incorporate mass without producing observable radiation. The object does not heat up. It does not glow. It does not emit detectable waves. It merely incorporates the absorbed matter into the calibration of its shell, subtly adjusting the structure and resonance of its layers. If a spacecraft were to drift into a Gravastar, the event would be horrifyingly anticlimactic. There would be no violent spaghettification, no dramatic plunge, no visible explosion. The ship and its crew would simply vanish, reduced to quantum noise at the surface. Even stranger, the process would be completely silent. No radio signals would escape, no distress transmissions, no energy spike. The Gravastar would consume the mass and continue drifting through space as if nothing had happened. But while the shell remains quiet, the environment around a Gravastar may tell a different story. As matter approaches the boundary, strange gravitational anomalies occur, shifts in spacetime that can produce unpredictable movements in nearby objects. Stars may wobble, gas clouds might twist into spiral patterns, dust rings could distort into asymmetrical shapes. These anomalies might last for mere minutes or persist for thousands of years, depending on the Gravastar's configuration and the nature of the infalling matter. One of the most disturbing scenarios involves a Gravastar interacting with a star. If a Gravastar passes near a star, the gravitational tug-of-war can destabilize the star's fusion processes. The outer layers may be stripped away, drifting silently into the Gravastar's quantum horizon. Over time, the star may dim, collapse, or even explode not because of a supernova, but because its equilibrium has been disrupted by a dark, invisible intruder. In regions densely populated with stars such as galactic centers or globular clusters, Gravastars could act as cosmic voids, quietly draining material and altering stellar evolution. Planets caught in the gravitational influence of a Gravastar might behave even more unpredictably. Their orbits could shift abruptly, causing catastrophic climate changes or planetary collisions. A Gravastar passing through a solar system would not announce its presence with light or heat. Instead, planets would begin drifting, moons might break free, and asteroid belts could collapse into chaotic streams. And yet there would be no visible culprit, only the silent pull of an object that emits nothing. If a Gravastar ever approached the outskirts of a system like ours, the first signs would be subtle. Long-period comets might shift off their usual trajectories. The Oort cloud could ripple with gravitational waves. Over decades or centuries, the orbits of distant objects might begin to deform. By the time the disturbance reached the inner planets, it would be too late. The Gravastar would not collide with anything. It would simply pass through the region, reshaping or destroying everything in its path through gravitational influence alone. Even its departure would be silent. The planets it leaves behind would drift in new, unstable orbits, whole systems quietly rearranged or thrown into long-term chaos. Another terrifying possibility involves the Gravastar's potential to trigger false signs of dark matter. Because Gravastars interact with the universe purely through gravity, their presence could be mistaken for unseen masses or dark matter halos. Scientists observing galaxies might detect gravitational effects with no visible source and attribute them to dark matter distributions, unaware that a Gravastar is drifting through the region. This raises an unsettling question. How many gravitational anomalies currently attributed to dark matter are actually the fingerprints of Gravastars? If these objects are common, they may be influencing the structure of galaxies far more than we realize. They could be hiding inside spiral arms, perched at the edges of galactic voids, or drifting through interstellar space like silent predators. Their interactions with normal matter would remain invisible unless observed with extreme precision, and even then the signals might look like noise. The reality is simple and terrifying. A Gravastar can move through the universe consuming matter, altering orbital dynamics, destabilizing stars and distorting space, all without producing a single photon of detectable light. It is a cosmic eraser, a silent engine of gravitational influence. And the worst part is that, unless it passes close enough to directly affect us, we may never know it was there at all. If Gravastars truly drift through the universe in significant numbers, then one of the most unsettling questions becomes this. What happens when a Gravastar and a black hole encounter each other? These two objects, both born from the collapse of massive stars yet fundamentally different in nature, represent opposing extremes of physics. A black hole is a region where spacetime caves inward infinitely, pulling everything toward a singularity. A Gravastar, on the other hand, is a hollow bubble of repulsive vacuum pressure, wrapped in an exotic shell that resists collapse with quantum force. When such radically different objects collide, the outcome would not resemble any known astrophysical event. Imagine a massive black hole drifting through space, absorbing gas clouds and stars, curving space-time with its crushing gravitational field. Now imagine a Gravastar silently approaching, invisible yet dense, its shell vibrating with quantum resonance. The moment their gravitational fields overlap, the interaction becomes an unfathomable tangle of inward and outward pressures. A black hole tries to suck everything inward. A Gravastar pushes everything outward at its boundary. These competing forces create a region of violent instability, a turbulent interface where normal space-time begins to glitch. If the Gravastar passes nearby without direct collision, the objects might orbit each other for millions of years. Their gravitational dance would generate complex waves patterns, unlike those from merging black holes. Instead of a smooth rising chirp, the gravitational wave signal might jitter, stutter, or contain abrupt distortions caused by the Gravastar's layered quantum shell. These signals could already be buried in detection data, ignored because they don't fit any recognized pattern. But if the Gravastar ventures too close, the black hole's immense tidal forces begin pulling at the Gravastar's shell. The exotic layers stretch and shake but refuse to collapse. Black holes distort space-time, but Gravastars resist that distortion with quantum rigidity. The shell acts like a cosmic drumhead, vibrating violently as the black hole's gravity tears at it. These oscillations might release bursts of gravitational energy or strange exotic radiation, though none of it would be visible as light. Eventually, one of two main outcomes occurs. In the first scenario, the black hole dominates. Its gravitational pull overwhelms the Gravastar's outward pressure, ripping apart the exotic shell layer by layer. As each layer is consumed, the black hole experiences chaotic feedback brief moments, where space-time stretches disproportionately due to the shell's quantum nature. These fluctuations could cause the black hole to hiccup, momentarily changing the rate of its rotation or mass accretion. When the final layer collapses the Gravastar's interior, its chaotic inflationary vacuum erupts outward. But instead of creating an explosion, the the black hole absorbs the expanding vacuum instantly. That sudden intake of warped spacetime could destabilize the black hole's event horizon, creating odd ripples or distortions before it settles back into equilibrium. In the second scenario, something astonishing happens. The Gravastar survives. Instead of being consumed, its shell remains intact long enough to resist total collapse. The black hole's gravitational field compresses the Gravastar's layers, but cannot puncture the quantum boundary. If this occurs, the Gravastar may actually transfer energy to the black hole, similar to two resonating systems interacting. The black hole's rotation might slow, or its mass distribution may shift. The Gravastar could even bounce away, propelled by the compression of its inner vacuum. This rebound effect might send it hurtling across space at incredible speed. Some researchers believe that certain hypervelocity compact objects observed throughout the Milky Way might be Gravastars flung away from past encounters with black holes. An even more dramatic possibility suggests that the Gravastar's interior vacuum could destabilize the black hole's singularity. If the shell is forced inward, the exotic vacuum might merge with the singularity, causing it to inflate or transform into a different state. This could theoretically extinguish the singularity entirely, turning the black hole into a Gravastar-like structure. If this is possible, then Gravastars may not just coexist with black holes, they might convert them. This transformation would produce gravitational waves unlike anything seen before, with unpredictable shifts in rhythm or energy. The event would appear as a failed black hole merger, fizzled out halfway through, a cosmic anomaly that challenges the very idea of collapse. More speculative theories propose that when a Gravastar and a black hole collide directly, the two objects could merge into a hybrid structure, something neither purely gravitational collapse nor purely vacuum bubble. This new entity might contain the singularity from the black hole surrounded by the exotic shell of the Gravastar. Such a hybrid would be even more mysterious, a singularity insulated inside a quantum membrane, unable to interact normally with spacetime, trapped in an exotic prison. The universe might hold dozens of these hybrids, each one drifting silently, noticeable only through unusual gravitational signatures. A hybrid object could mimic a black hole, but with subtle anomalies such as inconsistent accretion behavior or gravitational lensing patterns that shift unpredictably. Some astrophysical observations already contain hints of such anomalies: black holes with unexpected masses, silent companions in binary systems, or gravitational wave events with strange spectral properties. Perhaps these are not errors. Perhaps the universe is already full of Gravastar black hole hybrids. The truth is, interactions between Gravastars and black holes might be among the most complex, violent, and invisible events in the cosmos, unseen, unrecognized, and buried within noise. And if these meetings shape galaxies or alter cosmic structures, then the deep history of the universe may have been partly written by collisions between objects we still cannot detect. While Gravastars themselves are terrifying enough, an even deeper and more enigmatic question arises when we consider how they might influence the evolution of galaxies and cosmic structures. For decades, astrophysicists have looked to black holes, especially supermassive ones, to explain the shape and motion of galaxies. But if Gravastars exist, they might be playing a hidden, foundational role in the architecture of the cosmos, quietly shaping the universe from behind a mask of perfect invisibility. Every galaxy contains a massive object at its center, assumed to be a supermassive black hole. These central giants anchor galaxies, their gravity-binding stars, gas, dust, and dark matter into spiraling structures. But some galaxies exhibit behavior that doesn't quite match known black hole physics. Their rotation curves are inconsistent, their central masses fluctuate unpredictably, or their energetic output is lower than expected. For years, scientists have attributed these discrepancies to observational error or uncertain dark matter models. But Gravastars offer another explanation. Some of these galactic cores may not be black holes at all. They may be enormous Gravastars, quietly stabilizing entire star systems without emitting the kind of radiation a black hole would produce. Supermassive Gravastars would behave like invisible anchors. They would exert gravitational control while producing no jets, no accretion noise, and no X-ray signatures. Their presence would make galaxies appear strangely calm. Their gravitational influence would be smooth, lacking the chaotic flares and bursts associated with black holes feeding on matter. A galaxy centered around a Gravastar might rotate cleanly, silently, and predictably for billions of years. If even a fraction of observed galactic centers contain gravastars, then our understanding of cosmic evolution needs to be rewritten. The universe may not be dominated by violent, luminous black holes as we once believed. It might instead be shaped by silent, hollow quantum objects acting as invisible hearts of entire star systems. The presence of gravastars could also explain several cosmic phenomena that currently lack satisfying explanations. Consider the mystery of ultra-diffuse galaxies as large as the Milky Way but containing only a few stars. Traditional models struggle to explain how these faint ghost-like structures form and survive, but if a gravastar exists at their center, its gravitational influence could bind a sparse collection of stars without producing the energetic chaos associated with a typical black hole. This would allow diffuse galaxies to remain stable without collapsing or dispersing. Gravastars might also serve as seeds for the earliest cosmic structures. In the young universe, before stars fully formed, collapsing energy fluctuations might have occasionally produced gravastars instead of black holes. These objects would then attract matter gravitationally, forming islands around them that later became early galaxies. If this process were common, gravastars may have been instrumental in shaping the first clusters of stars, acting as silent gravitational anchors long before the first luminous black hole began to feed. Another clue comes from dark galaxies, mysterious systems with almost no visible stars but strong gravitational influence. These galaxies appear to be made almost entirely of dark matter, yet they behave oddly, with mass distributions that don't match theoretical expectations. If a gravastar sits at the heart of these systems, its perfectly invisible nature would make the galaxy seem far more dominated by dark matter than it truly is. Gravastars might also play a role in regulating star formation. A typical black hole can trigger intense starbirth by compressing and heating nearby gas clouds through high-energy activity. A gravastar, by contrast, would remain completely silent. Gas would drift toward it without being heated or shocked, preventing the bursts of star formation that black holes often ignite. This could explain why some galaxies produce stars slowly or appear unusually quiescent despite having sufficient gas. Even the structure of galactic halos, those enormous invisible cocoons of mass-surrounding galaxies, might be subtly influenced by gravastars. Because gravastars do not emit energy, their gravitational pull could help maintain stable halo shapes, preventing the chaotic disturbances usually introduced by active black holes. On larger scales, gravastars might even alter the distribution of cosmic filaments, the massive threads of galaxies stretching across the universe. A gravastar passing near a filament could warp its structure without producing detectable radiation, subtly influencing the trajectory of galaxies for millions of light-years. There are also anomalies in the cosmic microwave background, tiny irregularities in temperature and density, that could, in theory, be remnants of ancient gravastars warping early spacetime. Some of these anomalies are too large or too structured to be easily explained by standard models. Gravastars might have created gravitational distortions that remain imprinted on the background radiation to this day. But perhaps the most extraordinary possibility involves what gravastars could mean for dark matter. If gravastars are far more abundant than black holes, their cumulative gravitational influence could account for a significant portion of the missing mass in the universe. In other words, what we call dark matter may not be a mysterious particle, but a population of invisible gravastars scattered across the cosmos. They would be indistinguishable from ordinary dark matter in many observations since they do not radiate. But unlike dark matter particles, gravastars are massive objects capable of shaping cosmic structure more effectively than diffuse clouds of unknown material. If this hypothesis is true, then the universe might be filled with countless gravastars acting as stepping stones of hidden gravity, weaving a web of influence that holds the cosmos together. Galaxies might orbit around these invisible nodes. Clusters might form in their wake. Entire regions of the cosmos might be sculpted by the silent geometry of gravastar populations. And all the while, humanity would remain unaware, mapping the heavens under assumptions that ignore the possibility of these quantum titans. Gravastars may not merely exist in the universe, they may be one of the fundamental architects of its shape. If gravastars are truly scattered throughout the universe, shaping galaxies and silently influencing cosmic evolution, then the next question becomes unavoidable. Could these objects ever become unstable? The outward quantum pressure inside a gravastar balances perfectly against gravitational collapse, creating a delicate equilibrium unlike anything else in astrophysics. But delicate does not mean permanent. In fact, many theoretical models warn that gravastars might be inherently unstable, under certain rare conditions, instabilities that could transform them into some of the most destructive objects in the universe. The stability of a gravastar depends on the precise tension between its internal vacuum energy and the strength of its exotic outer shell. If this balance shifts even slightly, the entire system could spiral into chaos. The shell might buckle, wrinkle, or fracture, the interior vacuum might surge outward, or the layers could collapse inward, creating a catastrophic chain reaction. The most straightforward failure mode is shell collapse. If the exotic matter making up the shell loses its rigidity or becomes disrupted by a powerful external force, such as a collision with a neutron star, a tidal encounter with a supermassive black hole, or an intense gravitational wave, the shell might fold inward. Once the first layer destabilizes, the others follow almost instantly, collapsing like a stack of dominoes. When this happens, the interior vacuum loses containment. In less than a microsecond, the suppressed inflationary energy at the core erupts outward. But unlike a supernova, where matter explodes in a burst of light and radiation, a gravastar detonation releases mostly exotic energy and gravitational shock. The result could be a type of explosion that leaves no visible signature yet sends out a devastating gravitational pulse, capable of disrupting stars and planets across vast distances. Some physicists believe that such an event could mimic the merging of ultramassive black holes or produce gravitational wave bursts so brief and chaotic that detectors dismiss them as noise. Another catastrophic scenario involves vacuum decay. If the interior vacuum exists in a metastable state, balanced on the edge of a more stable configuration, then a sudden disturbance could trigger a transition. This transition would propagate outward at nearly the speed of light, converting the interior into a lower energy vacuum state. In normal circumstances, such a vacuum transition would be contained by the shell. But if the shell cracks or fails during the event, the new vacuum could spill into the surrounding universe. This is not just an explosion. It is a local rewriting of physics, a tiny region where the laws of nature are replaced with a different set. Even a small breach could release enough exotic energy to tear open a bubble of altered spacetime, a region where fundamental constants shift and the structure of matter disintegrates. In theoretical physics, such an event is often called a false vacuum decay, and it is considered one of the most terrifying doomsday scenarios imaginable. If a gravastar catalyzes such a decay event, the expanding bubble could annihilate everything in its path, converting the universe into a new, incompatible configuration. Thankfully, most models assume gravastar shells are strong enough to prevent such a catastrophe. But the possibility exists, and that alone changes how we think about these silent objects. Another form of instability is resonance buildup. Gravastars are essentially cosmic drums, with their shells vibrating at precise frequencies controlled by quantum interactions. If external gravitational waves match one of these resonant frequencies, the gravastar could begin absorbing energy like a tuning fork struck repeatedly. Over time, the vibration amplitude might increase, stressing the shell. If resonance grows beyond the shell's tolerance, it could shatter abruptly. In this case, the gravastar would erupt in an explosive release of gravitational energy, producing a massive wave that sweeps across space. Stars could be jostled from orbit, planets could be stripped of atmospheres, entire systems might experience distortions in space-time, and yet, because the energy is released as gravitational disturbance rather than visible radiation, the event might be nearly invisible except to advanced detectors. Even collisions pose unusual risks. If two gravastars collide, their shells could interfere destructively. Layers might tear apart, merging or rupturing in unpredictable ways. The combined interior vacuums could destabilize instantly, unleashing a burst of exotic energy far greater than any supernova. The result might be the closest thing the universe has to a pure gravitational explosion, a violent rearrangement of space-time that leaves no debris, no light, and no aftermath except warped geometry and disrupted orbits. Gravastar instability also raises an interesting possibility. Could these events be responsible for unexplained high-energy phenomena in the universe? Some gamma-ray bursts appear far too powerful to fit known models. Some gravitational wave signals lack the expected signatures of merging neutron stars or black holes. Some fast radio bursts appear to originate from completely empty regions of space. If gravastars exist and occasionally destabilize, they could explain these anomalies. The universe is littered with strange, unexplained flashes, ultra-fast bursts lasting milliseconds, gravitational distortions with no visible source, or sudden spikes in cosmic energy that appear out of nowhere. All of these could be fingerprints of gravastars reaching their breaking point. But perhaps the most chilling instability arises not from external forces but from time itself. The interior of a gravastar may evolve slowly, with vacuum energy shifting subtly over billions of years. Eventually, the equilibrium that keeps the shell intact could decay naturally. If this happens, the gravastar's end would come without warning, a sudden release of its suppressed inflationary core, a silent eruption across the galaxy. It would be a death with no light, no fire, no visible explosion, only a wave of gravitational chaos expanding outward like a ghost. A silent ending for a silent object. And somewhere, perhaps in our own galaxy, gravastars billions of years old may be quietly approaching that final moment. If gravastars represent one of the deepest cosmic mysteries, then the possibility that advanced civilizations could interact with, or even harness them, pushes that mystery into a realm bordering on science fiction and theoretical megastructure engineering. Yet if gravastars truly exist, and if they possess the bizarre quantum properties many models predict, then any sufficiently advanced species might see them not as threats, but as opportunities. To such a civilization, a gravastar is not a monster, it is a natural engine, a reservoir of exotic energy, a stable quantum boundary, and potentially one of the most powerful tools the universe can offer. The first and most obvious use would be energy extraction. Traditional methods of harvesting cosmic energy rely on stars, black holes, or accretion disks. But a gravastar could provide something far more exotic: direct access to vacuum energy. The shell of a gravastar holds unimaginable amounts of trapped quantum energy, compressed and stabilized by its layered structure. If an advanced species learned to interface with the surface, perhaps by manipulating its quantum resonances or tuning into its vibrational modes, they might siphon off energy on a scale far beyond stellar output. This would effectively transform the gravastar into a hyper-efficient power source, one that produces no radiation, no pollution, and no detectable emissions. For civilization-level engineering, this is the holy grail: limitless silent power. Such a system could drive interstellar propulsion, sustain artificial habitats, or feed planetary-scale industries. The gravastar would remain externally invisible, offering a perfectly stealthy power source that would leave no signature detectable by external observers. This leads to another profound possibility. Gravastars could serve as hubs for cloaked civilizations. If a society built structures around a gravastar habitats, stations, or even entire cities, they could hide in its gravitational shadow. The gravastar emits no light, no heat, and no detectable activity. Technologies built within its gravitational well would be shielded from detection by conventional astronomy. To an outside observer, the region would appear empty. No radiation, no thermal output, nothing to suggest life. In this sense, gravastars could act as cosmic hideouts, natural cloaking devices for advanced species seeking to remain unseen. Some have speculated that this could explain the Fermi paradox. Perhaps civilizations cluster around gravastars to remain invisible, harnessing their exotic properties while avoiding detection. Beyond energy and concealment, gravastars might serve as gateways for manipulating spacetime itself. Their exotic shells produce complex, self-stabilizing quantum geometries properties that could be exploited for advanced propulsion, or even wormhole construction. The oscillations in the shell might be tunable, allowing an engineered interface to redirect or amplify gravitational waves. With fine control, this could enable faster-than-light communication channels based on space-time deformation rather than radio waves. Another speculative idea is that the interior vacuum of a gravastar could be accessed or manipulated by adjusting the shell's resonance. If the hollow core truly behaves like a miniature inflationary universe, a bubble of warped space-time with unique physical properties, then controlling the boundary might allow access to a new kind of computational environment. A civilization could use the interior as a quantum processor, storing information in a vacuum that evolves according to different physical laws. This would create a computing system capable of running simulations far beyond the capability of ordinary hardware. The Gravastar itself would function as a universe-scale quantum computer, potentially able to process information at speeds and densities unimaginable to biological minds. Some theories even suggest that the internal vacuum could support exotic forms of time manipulation. If the interior contains zones where time moves differently or loops in closed patterns, a sufficiently advanced species could exploit these effects for temporal computation, long-term data storage, or even controlled time experiments. The mind-bending part is that all of this would occur inside a completely invisible structure, drifting silently through space. The implications are startling. Humanity might be searching for alien megastructures among stars and Dyson spheres, while the most powerful and advanced civilizations could be hiding inside Gravastar systems we mistake for empty voids. Gravastars may also offer unprecedented defensive capabilities. A civilization that learned to manipulate the shell could potentially redirect incoming energy, absorb radiation, or convert harmful impacts into harmless quantum noise. In essence, the Gravastar could serve as an impenetrable fortress. No missile, no beam, no cosmic threat could breach its boundary. Even a planetary collision might be harmlessly absorbed into the shell, vanishing with no trace. This would render the civilization effectively invulnerable to natural disasters or hostile forces. Additionally, Gravastars might be used as anchors for stabilizing wormhole networks. Their quantum shells provide a perfectly rigid, self-healing structure that could theoretically hold open the throat of a wormhole without collapsing. If so, Gravastars might function as the hubs of an interstellar transportation grid, enabling instantaneous travel across regions of space connected through gravitational geometry. And then there is the most unsettling speculation. What if some Gravastars are not natural at all? What if they are engineered objects, artificial structures created by civilizations that surpassed even Type 3 on the Kardashev scale? A Gravastar's exotic shell, its hollow vacuum core, and its perfect invisibility could all be attributes of a designed object rather than a natural one. Such megastructures could serve as storage units for enormous amounts of energy, as nodes for galaxy-spanning infrastructure, or as computational cores housing the minds of long-extinct species. Humanity would have no way of knowing. A Gravastar would appear indistinguishable from a black hole in most observations. It would emit nothing. It would reveal nothing. Yet inside, a civilization could thrive, evolve, and work with technology so advanced that the Gravastar becomes both a fortress and a machine. The possibility that Gravastars may not only silence stars but also shelter civilizations adds a new layer of mystery to these cosmic phantoms. Perhaps somewhere in the universe, hidden inside one of these silent objects, ancient intelligences still listen, think, and wait. If Gravastars are as enigmatic and invisible as theory suggests, then the question becomes, how could humanity ever detect them? Modern astronomy relies heavily on electromagnetic signals, light, radio waves, X-rays, gamma rays, to understand the universe. But Gravastars give off none of these. They emit no light, generate no heat, and release no detectable radiation. They are cosmic voids masquerading as empty space. This forces us to reconsider not only how we observe the universe, but what we've been missing all along. The first method scientists might use to identify Gravastars involves gravitational signatures. Although Gravastars mimic black holes in many ways, their mass distribution can be subtly different. A black hole funnels all its mass into a singularity, creating a specific gravitational profile. A Gravastar spreads its mass across a shell, producing a gentler, slightly flatter curvature of spacetime. These differences are faint, but with sufficiently precise observations, especially of orbiting stars, we might detect anomalies. For example, a star orbiting what we believe to be a black hole might show tiny deviations in speed or trajectory. Instead of following a perfect elliptical orbit, the star could oscillate, wobble, or experience periodic shifts that don't align with black hole physics. These irregularities would be microscopic, detectable only by the most sensitive instruments. Yet if measured over long time frames, they could reveal the telltale drum-like vibration patterns produced by a Gravastar's shell. Another potential method is gravitational lensing. Black holes bend light in a distinctive way, creating sharp, symmetrical arcs, or glowing rings around their event horizons. Gravastars, however, can produce lensing patterns that are subtly distorted, Because there is no singularity and no event horizon, the warped light around a gravastar may form asymmetric arcs, stretched shapes, or faint halos instead of a defined shadow. The effect is delicate, but future telescopes with exceptional resolution might be able to distinguish between a true black hole shadow and the ghost-like curvature of a gravastar. Even so, lensing alone would not be definitive proof. We would need to combine observations from multiple wavelengths and gravitational studies to build a consistent case. A more promising tool is gravitational wave analysis. Black hole mergers create incredibly specific wave signatures, a sharpened spiral, a rising chirp, and a predictable ringdown. These waveforms are elegant and mathematically precise, but if two gravastars collide, or if a gravastar merges with a black hole, the resulting wave would be far more chaotic. Instead of a smooth, ringing decay, we would hear something irregular, a series of distortions, sudden spikes, or oscillations representing the shell layers tearing, rebounding, or vibrating during the collision. Current detectors may have already captured such events, only to categorize them as data anomalies or sensor noise. As detection technology improves, researchers may revisit old data and realize that some noise had structure that matches gravastar models. Another method involves studying regions where mass seems to be present but produces no electromagnetic signal. Dark matter is often used to explain such phenomena, but if clusters of gravastars exist, their gravitational pull could masquerade as dark matter halos. If scientists map a region and discover localized gravitational distortions that cannot be explained by black holes, neutron stars, or dark matter distributions, gravastars could be the missing ingredient. Yet this still leaves a major challenge: how to confirm a gravastar rather than simply suggest one. One potential distinguishing feature is how matter behaves near the surface. When matter falls into a black hole, intense radiation is produced at the accretion disk. A gravastar has no such disk. If astronomers discovered a region where matter vanished without producing heat or high-energy emissions, this would strongly imply a gravastar. Imagine a star losing mass, but without any visible jets, flares, or radiation bursts. Imagine gas clouds disappearing without heating up. Imagine a star orbiting an apparently empty region, slowly being drained of its atmosphere with no visible mechanism. These would be unmistakable signs of gravastars. Even more compelling would be detecting the vibration modes of the shell itself. Gravastars have theoretical oscillation frequencies that differ from those of black hole event horizons. If gravitational wave detectors captured periodic pulses matching these hypothetical frequencies, it would be as close to a gravastar fingerprint as physics could hope for. Another avenue involves searching for subtle echoes. When black holes merge, the resulting gravitational waves fade smoothly as the new singularity stabilizes. But if a gravastar is involved, the waves may reflect off its shell, creating faint secondary ripples, echoes occurring milliseconds or seconds after the main event. Several studies have already reported unusual gravitational wave echoes following black hole mergers, but the data is currently inconclusive. Some scientists argue they are artifacts, others believe they might be the first hints of gravastars hiding in the universe. The most ambitious detection method would require entirely new physics, technology capable of sensing quantum fluctuations or exotic matter directly. If future instruments can detect anomalies in vacuum energy or deviations in quantum field behavior, gravastars might stand out as regions where the vacuum behaves strangely. Regions where the laws of physics shift slightly near a surface thinner than an atom. Ultimately, gravastar detection hinges on recognizing what is missing. No light, no jets, no radiation, no accretion, no supernova remnants, only gravity, silence, and subtle distortions. In a universe filled with noise, gravastars are the quietest objects of all. And perhaps that is why we have struggled to find them. We have been listening for thunder while gravastars whisper in gravitational tones too faint for our primitive instruments. But as technology advances, the universe's silent giants may finally reveal themselves, not with an explosion of light, but with the soft tremor of warped space-time. If gravastars lurk in the silent darkness of space, undetectable, impenetrable, and possibly plentiful, then the next question is almost unavoidable. Could they ever pose a direct threat to intelligent civilizations? Not through malice, of course, but through sheer physical existence. For all their elegance as theoretical objects, Gravastars are essentially perfect cosmic traps. They give no warning signs, announce no presence, and leave no visible trace of their approach. A civilization could monitor its sky for centuries, chart every star with obsessive accuracy, and still fail to notice that a gravastar is drifting silently toward its planetary system. Unlike a black hole, a gravastar does not distort its surroundings dramatically until the last moment. There is no luminous accretion disk, no radiation jets, no gamma-ray bursts, no X-ray flares. The sky remains peaceful, the stars appear normal, and then, one by one, orbits begin to shift. The first signs would be subtle, so subtle that even an advanced society might dismiss them as sensor errors or rare gravitational perturbations. A comet's trajectory shifts by a fraction of a degree. The path of an outer gas giant wobbles slightly. A distant asteroid belt distorts, as if tugged by an invisible weight. Over the span of decades or centuries, the anomalies compound. The far reaches of the system become chaotic. Long-period comets begin appearing out of schedule. The gentle gravitational equilibrium that allowed planets to exist in stable orbits starts to erode. And still, there would be no luminous source to blame. To astronomers looking outward, the region would appear perfectly dark, perfectly empty. By the time the gravastar invades the inner zones of the system, the effects would intensify dramatically. Moons might drift out of orbit. Asteroid belts could collapse into chaotic streams of debris. Planetary climate systems would destabilize as orbits gradually warp. Tidal stresses would build, causing tectonic upheaval on the inhabited worlds. But because the gravastar emits no radiation or visible signatures, civilizations might not recognize the threat until the final stage, when the gravastar's gravitational pull becomes overwhelmingly dominant. At this point, salvation would be nearly impossible. The gravastar would not collide with planets. It would not destroy worlds through impact or explosion. Instead, planets would simply fall toward its gravity well, crossing the quantum horizon without producing any light, noise, or detectable energy. Entire civilizations would vanish silently, their worlds consumed by an object they could not observe, could not predict, and could not prepare for. This leads to disturbing speculation. Could gravastars be behind unexplained astronomical mysteries? Scientists have observed stars that dim suddenly or disappear entirely without supernova signatures. Typically, these anomalies are written off as dust clouds or observational issues. But gravastars offer a darker explanation, stars quietly sinking into invisible quantum shells. If a gravastar drifted through a stellar nursery, it could sterilize the region of new star formation without emitting a single photon. If it entered a densely populated star cluster, it could devour multiple stars over millennia, creating gravitational gaps and structural distortions that astronomers might incorrectly attribute to dark matter inconsistencies. And if a gravastar passed through a region containing inhabited worlds, those civilizations would be utterly helpless unless they possessed technology far beyond anything humanity currently imagines. Even worse is the possibility that gravastars might play a role in the long-term collapse of galaxies. A gravastar drifting through a galactic arm could destabilize entire clusters of stars, redirect dark matter flows, or alter the rotational dynamics of spiral arms. Over billions of years, such influences could reshape galactic structure in ways invisible to observers relying solely on light. There are also more speculative dangers. The quantum shell of a gravastar may be sensitive to extreme gravitational disturbances. A sufficiently energetic encounter, such as a collision with a neutron star, could destabilize the shell. If that happens, the gravastar might release a burst of exotic energy so powerful that it instantly sterilizes nearby star systems. The shock wave would not be light or heat, but a gravitational rupture, a distortion in space-time capable of tearing apart planets or collapsing stars. To any civilization in the blast radius, it would appear as if reality itself had momentarily glitched. No warning, no flash, no sound, just destruction. Even more unsettling is the possibility that gravastars could catalyze vacuum decay. If their interiors exist in a metastable false vacuum state, a catastrophic failure could trigger a transition to a lower energy vacuum. This event would not simply destroy a planet or star, it would rewrite the laws of physics in a rapidly expanding bubble. Inside the bubble, atoms could not exist, forces would behave differently, and matter itself would dissolve. Fortunately, most models suggest Gravastar shells are strong enough to prevent such a scenario from propagating. But the possibility remains an ever-present shadow over the concept of advanced cosmic engineering. Civilization-level danger aside, Gravastars also raise existential questions. Could an entire civilization perish without leaving any evidence because their star system was quietly erased by one of these objects? Could unexplained gaps in stellar populations, strange orbital anomalies, or missing planets in distant systems be the silent footprints of Gravastars passing through? Perhaps the night sky contains the aftermath of countless Gravastar encounters, events so quiet, so invisible, that only gravity remembers. Gravastars may not be predators in the traditional sense, but their mere existence makes them among the most dangerous objects in the universe. They do not choose to destroy, but they can erase worlds effortlessly and without warning. And the most terrifying part is this: unless a civilization understands Gravastars in advance, it would never even know what killed it. If Gravastars exist throughout the universe, silent, invisible, and potentially numerous, then one of the most profound implications concerns not destruction or cosmic engineering, but something far stranger: their possible role as cosmic archives. Because Gravastars convert all incoming matter into quantum information encoded in their shells, every object they consume might leave behind an imprint deep within the structure of their layers. This transforms Gravastars into accidental libraries of the universe, vast repositories of encoded patterns stretching back billions of years. Unlike black holes, which swallow information into a singularity where it seemingly disappears, Gravastars distribute what they absorb into the resonant frequencies of their shell. The layered structure becomes a record of everything that has ever touched it, not just matter, but light, gravitational fluctuations, magnetic fields, and complex energy signatures. Each interaction subtly reshapes the shell, embedding a microscopic alteration in its vibration modes. Over cosmic timescales, this could create an extraordinarily dense tapestry of encoded data. If an advanced civilization learned to interpret these patterns, they might unlock the histories of stars, planets, and even civilizational artifacts long destroyed. In theory, a Gravastar could store the quantum fingerprints of entire worlds. If a planet fell into a Gravastar 1 billion years ago, fragments of its atmospheric chemistry, geological history, electromagnetic transmissions, and even biological signatures could remain encoded in the shell structure. This does not mean that the planet's full image is preserved, but the Gravastar may retain enough information to reconstruct aspects of its existence, like faint echoes of a lost reality. This concept leads to a staggering possibility. Gravastars might be the universe's natural data vaults, preserving cosmic history long after stars burn out and galaxies fade. While life forms perish, civilizations collapse, and matter itself decays, a Gravastar's shell remains stable for trillions of years. Their stability could outlast even proton decay. In the distant future, when almost every structure in the universe has dissolved into darkness, Gravastars may still drift through the void, carrying within them the only surviving traces of ancient galaxies. For any advanced species seeking knowledge of the universe's past, Gravastars could be invaluable. They would be the last witnesses of cosmic evolution. But accessing this information would require unimaginable levels of technological sophistication. A civilization would need to interface with the exotic shell without destabilizing it. They would need to decipher complex quantum oscillations that shift trillions of times per second. They would need to map layers thinner than atoms, each containing vibrations encoded by processes that stretch back to the early universe. And even if they could decode this data, the information might not be literal. It might resemble a shattered puzzle of physics, energy patterns, and quantum events that requires interpretation rather than direct reading. But this raises another possibility. What if someone has already done this? What if certain Gravastars have been intentionally modified by advanced civilizations to store information deliberately? Imagine a species facing extinction, realizing their worlds are doomed by cosmic catastrophe. Instead of building monuments or sending messages into the void, they might encode their knowledge into the shell of a Gravastar, trusting that the object will survive long enough for someone else to discover it. This would create a cosmic time capsule, impervious to decay, radiation, entropy, or the death of the universe itself. If civilizations regularly encoded data into Gravastars, the universe might be filled with these silent vaults, each containing compressed knowledge from species long gone. We would never recognize them because they look identical to naturally formed gravastars. They radiate no signal. They emit no artificial patterns detectable with primitive technology. Yet within, they might hold messages from civilizations older than our entire galaxy. Even more extraordinary is the possibility that gravastars could be used intentionally as communication tools. Their shells can resonate with gravitational waves. If manipulated, these oscillations might transmit information across cosmic distances. Because gravastar shells are extraordinarily stable, these transmissions could persist for eons. If a civilization wanted to send a message to the future far beyond the lifespan of any star encoding it, intergravastar vibrations might be the only viable method. This leads to a chilling speculation. Could some unexplained gravitational wave anomalies be encoded messages from ancient beings? If so, we currently lack the deciphering framework to interpret them. Another consequence of this archival behavior is the potential for unintended reconstruction. If an extremely advanced civilization extracted information from a gravastar, they might accidentally reconstruct fragments of extinct biospheres or cultures. This would be akin to pulling faint ghost images from quantum patterns, echoes of lives long erased by cosmic processes. These reconstructions would not bring the beings back, but they could reveal aspects of their technology, biology, or culture. Gravastars in this sense could serve as the only windows into the histories of civilizations wiped out billions of years ago, civilizations that left no material artifacts or detectable signals. They could also hold signatures of cosmic phenomena that no longer exist. Waves from ancient supernovas, imprints from the earlier stars, distortions from galactic collisions now long forgotten. The universe forgets almost everything. Entropy erases memory on every scale, but gravastars resist entropy better than almost any known structure. They may be the last objects capable of containing the memory of what once was. And so, while gravastars are terrifying for their power and invisibility, they may simultaneously be the most valuable repositories in the cosmos. They are tombs, but also libraries, silent destroyers, but also silent historians. They carry within them the quantum ghost of everything they have ever touched. And if a species someday unlocks their secrets, they may uncover not only the past, but truths about the universe that no other object could possibly preserve. If gravastars truly act as cosmic archives, accidental or intentional, then a deeper, more philosophical question emerges. What role do they play in the grand structure of the universe itself? Are they simply rare, exotic remnants of stellar evolution? Or could they be fundamental components of cosmic architecture? Some theorists suggest that gravastars might be a natural part of the universe's life cycle, serving functions far more intricate than those of ordinary stars or black holes. To imagine this, one must consider that the universe is not static. It evolves, adapts, and possibly regulates itself. Certain cosmological models propose that the universe behaves like a dynamic system seeking balance. Radiation disperses, matter clumps, stars ignite and extinguish, black holes form and evaporate. Gravastars may fit into this cycle as regulators objects that limit runaway collapse while storing the information necessary for future cosmic states. Unlike black holes, which swallow matter into singularities where physical laws break down, gravastars stabilize collapse in a controlled fashion. They halt gravity's inevitable descent into infinite density and instead create a hollow, balanced structure that preserves information across cosmic timescales. In this sense, gravastars could be nature's way of preventing spacetime from tearing itself apart. They cap the extremes, moderating the universe's most violent processes while maintaining coherence. But deeper theories push the idea even further. Some physicists speculate that gravastars might be seed structures for the next universe. Their interiors contain vacuum energy, an inflating space akin to the earliest moments of the Big Bang. If their shells were to rupture or decay at the right moment, that interior could expand outward, birthing a new cosmos. This would mean gravastars are not just leftovers of dying stars, but embryonic universes waiting for the right conditions to emerge. In this view, each gravastar is a potential Big Bang, wrapped in an ultra-thin cocoon, drifting unnoticed through our own universe. If such a rupture happened, the expansion would occur internally. From our perspective, the gravastar might simply vanish. But inside, a new universe would begin, complete with its own space-time, fundamental particles, and physical laws. This concept, known as cosmological natural selection, or multiverse budding, implies that gravastars are cosmic seeds, quiet, unassuming, and possibly abundant. Our universe could itself be the interior of a gravastar formed in a parent universe, long since faded or collapsed. If so, gravastars become more than astrophysical curiosities. They become the reproductive organs of the cosmos. Another speculation concerns dark energy. The mysterious force accelerating the expansion of the universe has baffled scientists for decades. Some have theorized that gravastars might contribute to this effect. Their interiors are filled with vacuum energy, sometimes called dark energy, held in place by the shell. If gravastars exist in massive numbers throughout the universe, their combined vacuum contributions could influence cosmic expansion. This would mean that gravastars are not simply isolated anomalies, but contributors to the large-scale behavior of spacetime. Their silent presence could shape the fate of galaxies, clusters, and voids, subtly pushing the cosmos outward. The universe, then, may be scaffolded by gravastars' quiet anchors that stabilize its expansion. They would be to the universe what seeds are to a forest, hidden, persistent, and essential to its evolution. Some models even propose that gravastars may be connected through quantum entanglement. Because their interiors contain uniform vacuum states, they might share a kind of quantum harmony across large distances. Disturbances in one gravastar could subtly influence others, creating a faint but universal network of spacetime regulators. This is not communication in a conventional sense, but a deep underlying coherence like tuning forks resonating across galaxies. A civilization advanced enough to sense or manipulate these resonances might gain unprecedented insights into cosmology. They might use gravastars to detect distant cosmic events before light or gravitational waves reach them. They might even use the network to stabilize wormhole systems or maintain galactic structures. In this sense, gravastars could be the universe's own distributed infrastructure, a quiet backbone of quantum geometry. There are even more exotic ideas. Some theories suggest gravastars may evolve over time, slowly adjusting their shell tension, mass distribution, or internal vacuum state in response to cosmic conditions. If true, gravastars might represent the closest thing the universe has to living structures, not alive in the biological sense, but adaptive, stable, and self-regulating. They might act like cosmic sponges, absorbing excess entropy or smoothing irregularities in spacetime. They might even prevent certain catastrophic instabilities from cascading across galaxies. To humans, these properties appear almost miraculous, but in the universe's language of quantum fields and gravitational geometry, they may be nothing more than natural processes we do not yet understand. There is also the possibility that gravastars influence the formation of galaxies. A gravastar forming early in cosmic history could serve as a gravitational anchor, drawing matter inward without emitting harmful radiation. This could aid the formation of supermassive structures at the centers of galaxies. In this model, some black holes at galactic centers may actually be gravastars. If so, entire galaxies might be built around the silent shells of ancient collapsed stars. Their presence would shape spiral arms, regulate star formation, and stabilize galactic rotation curves, processes currently attributed to dark matter or poorly understood dynamics. Gravastars would be the hidden architects of galactic structure, silent, invisible, untouchable, and essential. These ideas may seem speculative, even fantastical. But the more we examine the universe's unexplained phenomena, the more gravastars seem to offer coherent answers. They may be archives, seeds, regulators, anchors, and stabilizers all at once. Not because they were designed to be, but because the fundamental physics of their structure naturally leads to these effects. In the end, gravastars force us to confront a humbling possibility, that the universe is far more complex, far more interconnected, and far more self-organizing than we ever imagined. And gravastars, these hollow, silent objects drifting through the dark, may be the key to understanding it all. If gravastars truly occupy a hidden but fundamental place in the architecture of the cosmos, then humanity must also consider a more personal question. What would it be like to encounter one directly? Not through telescopes or simulations, but up close, far closer than any civilization should ever risk. Imagine a deep space exploration mission venturing into the unlit regions between stars, navigating through the cosmic void in search of new worlds or scientific discoveries. The crew charts gravitational fields, tracks stellar remnants, and monitors radiation signatures. Everything appears normal until it isn't. Their instruments begin registering subtle anomalies. The ship's inertial sensors detect tiny distortions that do not align with known masses. Light from distant stars seems to warp ever so slightly, bending in ways that defy standard gravitational lensing patterns. The region looks empty, yet space itself feels wrong, as though it is being tugged by something enormous and invisible. At first, the anomalies are so delicate that the crew might dismiss them as sensor drift or calibration issues, but then the distortions intensify. Trajectory calculations start requiring minuscule but persistent adjustments. The ship's navigational AI flags gravitational irregularities that cannot be explained by dark matter or distant stars. It is as if the ship is passing through the outskirts of an unseen gravitational well. Gradually, the reality becomes undeniable. They are approaching a massive object that emits no light, no heat, no radiation. For any observers, this moment would be terrifying, not because of what they see, but because of what they don't. The Gravastar would appear as pure darkness, not even a silhouette against the stars. It would be a hole in perception, a featureless sphere of perfect absence. There is no shimmer, no glow, no accretion disk. Nothing hints at its boundary until it is far too late. As the ship drifts closer, space around it grows increasingly distorted. Distant starlight bends and stretches, forming faint arcs around the invisible sphere. The Gravastar's gravity is not as extreme as a black hole's at equivalent distances, but up close, the tidal forces become disturbing. Large objects might crack, twist, or crumble under competing gravitational gradients. Inside the ship, artificial gravity fluctuations ripple through the decks. The crew begins to feel phantom forces, subtle pulls, and disorienting shifts in spatial perception. The navigation systems struggle to compute a safe trajectory, because the Gravastar's mass is spread across a rigid shell rather than concentrated at a singular point. This creates unpredictable micro-distortions, like gravitational fingerprints etched into the surrounding emptiness. If the ship accidentally crosses too close to the Gravastar's boundary, its quantum shell, the consequences become far more severe. Unlike a black hole's event horizon, which marks a point of no return, a Gravastar has a hard surface, a thin, exotic layer of ultra-dense matter. If a spacecraft collided with it, the impact would be catastrophic. But even without touching the surface, the ship might encounter quantum anomalies radiating from the shell. Sensors could begin to fail. Communications might degrade, not from interference, but from subtle distortions in the quantum fields holding the signals together. Timekeeping devices based on atomic oscillations might fall out of sync by tiny but unsettling amounts. These disturbances would grow stronger the closer the ship approaches the Gravastar. The crew might observe strange phenomena, lights flickering, instruments misreading values, or external cameras capturing warped imagery, reminiscent of optical illusions. In extreme proximity, even the vacuum itself seems unstable, as though space is vibrating with inaudible frequencies. But the truly horrifying risk comes from the Gravastar's ability to absorb matter without producing an accretion disk. A spacecraft straying too close would simply vanish into the shell, no explosion, no flash, no flare. It would disappear silently, its atoms pulled apart and its mass encoded into the Gravastar's layered structure. From the outside, it would look like the ship was swallowed by darkness. No one watching from a distance would ever know what happened. Even attempts at emergency escape might fail, because Gravastar gravity wells are uniquely deceptive. Their pull is gentler at far distances but becomes alarmingly steep near the surface. A spaceship could believe it has sufficient velocity to escape, only to discover too late that it has crossed a threshold where escape becomes impossible. Not because of an event horizon, but because the gravitational gradient is too steep for any engine to overcome. These properties make Gravastars uniquely dangerous for exploration. They cannot be detected visually. They do not produce radiation. They do not warn of their presence until a ship is nearly upon them. They are cosmic traps that lure explorers not through intent but through perfect silence. If humanity ever expands into interstellar space, Gravastars might become one of the greatest navigation hazards. Entire fleets could vanish simply by drifting too close to something they never saw. And yet, for all that danger, the scientific temptation would be irresistible. A gravastar offers insights into the nature of spacetime, quantum fields, and cosmic evolution that no other object can. The first civilization to directly study one might unlock physics humanity has never imagined. But to do so safely, they would need instruments capable of detecting gravastar signatures from extraordinary distances, gravitational wave reverberations, quantum field fluctuations, or distortions in vacuum energy. Without such technology, gravastars will remain deadly enigmas drifting unseen through the universe. In the end, encountering one up close would be both the most enlightening and the most lethal experience a civilization could ever have. The gravastar would reveal nothing. It would communicate nothing. It would simply exist, silent, immense, and indifferent to anything that comes near it. If gravastars pose such extraordinary risks and possibilities, then the final frontier of human understanding lies in one question that overshadows all others. Could we create one? Not discover it, not approach it, but intentionally build a gravastar using our own technology, shaping space-time itself into one of the most exotic and mysterious objects in the universe. The idea may sound impossible, but then again, so did black holes, before we understood stellar collapse. Theoretically, the ingredients required to create a gravastar already exist inside the framework of known physics. An input of vacuum energy, a means of compressing matter to extreme densities, and a stabilizing structure of exotic material capable of resisting collapse. In practical terms, it would require manipulating the universe at a scale far beyond anything humanity can achieve today. But the blueprint astonishingly might be within reach of future civilizations. The most straightforward method involves guiding a massive star into a controlled collapse. Instead of allowing it to implode into a black hole, an advanced civilization could intervene at the exact moment before the event horizon forms. By injecting exotic matter or vacuum energy into the collapsing core, they could force the star into a gravastar configuration. In essence, they would catch the collapse at the last moment, redirecting gravitational forces into the formation of a hollow interior and a quantum shell. This process would require technological mastery over gravity and quantum fields that we cannot begin to imagine. Yet if such mastery existed, the benefits would be staggering. A civilization capable of creating gravastars would have near-infinite energy generation capability. They could tailor the shell's resonance properties, engineer a stable internal vacuum, and even fine-tune the gravastar's gravitational signature to suit their needs. It would be the equivalent of building a cosmic-scale reactor or power source that never runs out, never radiates danger, and remains stable longer than stars survive. More ambitious concepts involve constructing a gravastar from scratch, without relying on natural stellar collapse. This would require assembling an enormous mass of ordinary matter, compressing it to a density just shy of gravitational collapse, and injecting vacuum energy into its core while encapsulating the structure in layers of exotic matter. Such construction would resemble building a Dyson sphere, except instead of surrounding a star, the civilization would be surrounding a growing gravitational well, shaping its collapse like sculptors working with space-time instead of clay. The technological hurdles are almost beyond comprehension. Manipulating exotic matter alone is beyond our current physics. Creating a quantum-stabilized shell capable of resisting collapse requires materials with negative pressure or negative energy density substances that exist only in theoretical papers and quantum experiments. Yet the universe itself demonstrates that such structures are possible. Gravastars, if they exist, prove that nature can build them, and if nature can build them, then intelligence might someday learn to replicate the process. A civilization that builds gravastars would ascend to a level of engineering comparable to controlling the Big Bang itself. Why would anyone attempt such a feat? The reasons are as varied as they are profound. First, gravastar technology would provide unprecedented energy. Instead of extracting power from stars which eventually die, or black holes which emit dangerous radiation, a gravastar offers clean, limitless vacuum energy. Second, gravastars could serve as data preservation units, a society threatened by extinction due to war, natural catastrophe, or cosmic disaster might encode its knowledge into the shell of a gravastar, ensuring that its legacy survives for trillions of years. Third, gravastars could stabilize large-scale gravitational structures. An advanced civilization might seed them across galactic regions to maintain orbital stability, influence spiral arm formation, or regulate the motion of massive bodies. They would become tools for sculpting galaxies. Fourth, Gravastars could support wormhole infrastructure. Their rigid quantum shells might function as anchoring points, allowing the civilization to create a stable interstellar transportation network. The Gravastars would act as nodes, silent, invisible gateways between distant regions of space. Fifth, Gravastars could act as protective barriers. A civilization could build Gravastars as shields around important systems, creating gravitational wells that repel incoming threats or distort hostile signals. But the most daring use involves universe creation. A sufficiently advanced species might intentionally rupture the interior vacuum of a Gravastar, creating controlled expansions that birth pocket universes, new realms of spacetime with different physical laws. These micro-universes could serve as experimental environments or safe havens for digital or biological life. In this speculative future, creating Gravastars becomes a form of cosmic engineering more profound than terraforming or starlifting. It becomes a method for shaping the destiny of reality itself. Yet such power also carries risks. A failed Gravastar construction could trigger gravitational disasters, vacuum instabilities, or uncontrolled shell collapse. A miscalculation in vacuum energy injection might rupture space-time locally. If not executed perfectly, the endeavour could annihilate entire star systems. Even an advanced civilization would treat Gravastar creation with extreme caution. It would be the pinnacle of technological achievement, but also the most dangerous. For humanity, the idea remains far distant. We cannot yet manipulate gravity on any meaningful scale, nor can we produce exotic matter. But intellectual seeds have been planted. Our descendants, hundreds or thousands of generations hence, may look back at these theories as the first steps toward understanding how to shape space-time with intention, instead of merely observing it. And so, the idea of building a Gravastar is not fantasy just premature. In the long arc of cosmic evolution, intelligence grows, technology advances, and the universe reveals its deeper mechanisms. Someday, perhaps unimaginably far into the future, constructing a Gravastar may become as routine for advanced civilizations as building a power station is for us today. And when that day comes, humanity, or whatever we evolve into, may finally take its place among the architects of the cosmos. If Gravastars represent one of the deepest cosmic enigmas ever imagined, objects that blur the line between astrophysics, quantum geometry, and the very structure of the universe, then their greatest impact may not lie in what they are, but in what they force us to confront about ourselves. The existence of Gravastars challenges not only our scientific understanding, but also our philosophical foundations. They compel us to rethink creation, destruction, memory, purpose, and the role of intelligence in an indifferent cosmos. These mysterious hollow stars, silent, invisible, and nearly undetectable, act like mirrors held up to our ignorance. They show us how little we know about the mechanisms governing reality. They remind us that the universe is not obligated to be understandable, predictable, or comforting. It simply is. And Gravastars, in their eerie quietness, embody that truth. The more we study them theoretically, the more they force us to acknowledge that the cosmos might contain layers of complexity far beyond our current comprehension. For centuries, humanity has believed that the universe is mostly accessible to reason. Stars burn, planets orbit, galaxies rotate, black holes swallow light. Even the most exotic phenomena have seemed eventually to yield to scientific explanation. But Gravastars break this comforting illusion. They suggest that the universe may contain objects that operate according to principles we have barely begun to grasp, principles involving exotic matter, vacuum transitions, stability conditions, and quantum shells that challenge our intuition at every step. This realization is both humbling and empowering. Humbling because it reveals our limits, empowering because it implies that the universe is filled with unexplored frontiers, each waiting for minds bold enough to reach for them. Gravastars also force us to revisit fundamental questions about information and existence. If they truly store the quantum fingerprints of everything they absorb, then they may act as cosmic memory vaults, repositories of lost civilizations, vanished stars, ancient galaxies, and forgotten eras of cosmic time. In this sense, Gravastars transform destruction into preservation. A world falling into a Gravastar is not erased. It is converted into patterns embedded in the shell. To any being capable of decoding those patterns, the Gravastar becomes a library of lost worlds. Perhaps millions of years from now, when humanity or its descendants stand at the brink of cosmic extinction, Gravastars will remain as the final record of our existence, silent monuments drifting through a cold, dying universe long after Earth is gone. And then there is the question of agency. If Gravastars can be engineered, manipulated, or even created by advanced civilizations, then they may serve as tools of unimaginable power energy sources, communication hubs, information vaults, spacetime stabilizers, or seeds for new universes. This raises profound ethical questions. Should any species have the right to manipulate structures capable of influencing entire galaxies? Should intelligence shape spacetime itself, or is that a privilege reserved for the natural evolution of cosmic forces? Humanity already struggles with the consequences of manipulating its own planet. What happens when a civilization gains the ability to manipulate the fabric of reality? Gravastars also intersect with the cosmic loneliness implied by the Fermi paradox. If advanced civilizations hide their presence using Gravastar cloaking, or build infrastructures around them, or encode information within them, then our inability to detect extraterrestrial life may be due not to its absence, but to a fundamental misunderstanding of what to look for. We have been searching for radio waves and Dyson spheres technologies that might be primitive compared to what a billion-year-old species would use. Gravastars could be the megastructures of the truly advanced, invisible, silent, perfectly stable, and eternally enduring. The idea is unsettling but also exhilarating. It means the universe might be far more crowded with intelligence than we realize. We just haven't learned the language of Gravastars, the language of gravitational signatures, quantum oscillations, and vacuum resonance. Gravastars also force us to confront the ultimate destiny of the cosmos. If they truly contain embryonic universes within their interiors, then the multiverse might be a fractal chain of Gravastar births. Every universe may be the hollow core of a Gravastar from a previous cosmic generation. If so, our own existence is the result of a collapse event in a different realm, an explosion that looked like a silent disappearance from the outside, but like a big bang from within. This perspective transforms Gravastars from astrophysical curiosities into the engines of cosmic renewal. In the grand recursive structure of reality, they may be the wombs of universes. And if humanity ever reaches the stage where it can create or influence a Gravastar, we may become active participants in this chain architects not only of technology, but of reality itself. Ultimately, Gravastars symbolize the unknown. They represent the vast territory beyond current science, the frontier where imagination and mathematics meet. They remind us that the universe is still full of secrets that will only reveal themselves to civilizations capable of asking questions as profound as the cosmos itself. Gravastars are not simply objects. They are challenges, invitations, mysteries waiting for explorers bold enough to step beyond the limits of light and matter. They whisper to us across the darkness, "The universe is deeper than you think, and your journey has only begun."